Are you considering studying mechanical engineering? What is mechanical engineering? What kind of courses could you expect to take? What are the different subfields of mechanical engineering? What type of careers might you expect to go into? All that and more in this video. In short, mechanical engineering is the application of the principles and problem-solving techniques of engineering from design to manufacturing for any physical object. Mechanical engineers analyze their work using the principles of motion, energy, and force, ensuring that designs function safely, efficiently, and reliably. As a mechanical engineer, you can work on a wide variety of projects and industries which develop technologies which require core knowledge of motion, energy, and force. You could find yourself designing a prosthetic arm, the engine or braking system in your car, the air conditioner providing heating and cooling in your house, and the list goes on. Mechanical engineering can be broadly broken up into 4 different concentrations. Manufacturing engineers, also known as industrial engineers, are responsible for designing manufacturing systems and processes to obtain high-quality products. The idea of the assembly line revolutionized the US market in the early 1900s and allowed for products to be assembled faster and with less labor. The assembly line is one such process that a manufacturing engineer could find themselves working on. You could also work with an amusement park company to design the wait in line system for park rides. One of the most frustrating complaints for any park goer are the long wait times for a ride. You could work on figuring out how to design the most optimal waiting system to minimize line congestion. And of course, there is much more you can do as a manufacturing and industrial engineer. Automotive engineers are responsible for designing all the mechanical systems within a vehicle. This includes the car frame, the braking system, the steering system, and the combustion engine. What material should we design the car's frame with? How much does the material cost? How much will the car frame protect the driver against injury in the event of an accident? How is the fuel within the engine combusted? How much force does this resulting combustion apply to the piston? All these design problems are handled by automotive engineers. HVAC engineers are responsible for designing systems that maintain and apply heating, ventilation, and air conditioning to a building. What would our modern society be without air conditioning? HVAC systems are found everywhere from commercial homes, schools, offices, hospitals, stores, and airports. Robotics and mechatronics engineers are responsible for designing robotic systems such as autonomous vehicles, medical equipment, and drones. These types of engineers can work on the mechanical systems in these types of products, but are also known for designing the electronic components and performing some level of programming in these systems. It's a specialization which requires all 3 skills. In a typical mechanical engineering curriculum, you'll see a series of classes which can be categorized into one of the 4 different concentrations we just covered. A typical mechanical engineering curriculum will include mechanics, vibrations, thermodynamics, fluid mechanics, and system design. Then, on top of that, you can take additional elective courses that are more tailored towards your concentration. You'll first start out with your mechanics courses, which includes statics and dynamics. Mechanics is the study of force, deformation, motion, and the relations between them. Given some mechanical system and information about the forces being applied to such a system, we can use mechanics to make useful predictions about how the system will deform and how the system will move as a result of the applied forces. A mechanical system can refer to any tangible object such as a wheel, a gear, a car, a building, or a bridge. In your mechanics course, you will learn how to design such systems and learn how these systems will react when a force is applied to it. An example of a system you will learn how to design is a truss bridge. If the force of gravity is pushing down on the bridge, how will the bridge react? How will the force be distributed along each truss? Is the bridge strong enough to withstand the force of gravity? Will it break or deform? What about when cars drive over the bridge? What about when a river current below applies a force? You will learn all the techniques and equations for solving such mechanical systems. The core equation used for determining the system's response to a force is Newton's second law of motion, F equals ma, which states that a system's acceleration is proportional to the net force applied to it. You will also learn to distinguish between a static system and a dynamic system. In short, a static system is a system where the net force applied on it is zero. In other words, the system is not moving or is in constant motion. It is not accelerating. A dynamic system is a system with non-zero acceleration. In the static system, the force of friction pulling the block up is equivalent to the gravitational force pushing the block down. Thus, the block will not move. In a dynamic system, the force of friction is less than the gravitational force pulling the block down, so the block will accelerate down the ramp. The study of mechanics is further extended into the realm of vibrations, which is concerned with determining a system's response when under vibration. A vibration in a system is when oscillations occur about some equilibrium point. You will learn about the different types of vibrations and how Newton's laws can predict the behavior of such oscillating systems. How does the system vibrate when forces are applied to it? What is the frequency of the vibration? In other words, how fast does the system oscillate back and forth? In many instances, the vibration of the system is undesirable. It can result in wasted energy and wear and tear on the system. In this class, you will learn how to add dampers to such mechanical systems and learn how these dampers gradually dissipate the oscillating motion in the system. One example may include large buildings, which, in the event of an earthquake, can vibrate the building and cause significant damage, and in some instances result in the building collapsing. One such way to prevent this undesired oscillation is to use seismic dampers, which are used to absorb and dissipate the immense energy from seismic events, such as earthquakes. Next, you'll move on to your thermodynamics course, which, in short, is the study of the relations between heat, work, temperature, and energy. You will learn about the laws of thermodynamics and how they help predict the energy within a thermodynamic system when heat is transferred into the system and when work is done on the system. Examples of such thermodynamic systems include your refrigerator, the combustion engine in your car, the air conditioning unit in your home, and much more. Refrigerators use thermodynamics to remove heat from the inside of the refrigerator and cool it down. The coolant in your refrigerator, which can be a liquid or gas, is responsible for maintaining the temperature in the refrigerator's engine by absorbing heat from the food in the refrigerator and transferring that heat out into the air in the room. You'll learn all the techniques and equations for solving how energy is transferred in and out of such a thermodynamic system. You'll also learn about the concept of entropy, which is a measure of the level of disorder in a thermodynamic system. The second law of thermodynamics states that entropy always increases in a natural thermodynamic process. Another way to think about entropy is as a measure of the thermodynamic equilibrium in a system. If there is a temperature gradient between two systems, heat will flow from a warmer to a cooler system until they reach thermal equilibrium. Next, you'll move on to your fluid mechanics course, which, in short, is the study of fluids in motion or at rest. You will learn about the physics principles and equations which dictate the behavior of a fluid in a water distribution system, such as a system of pipes. For example, if water moves from a section of pipe with a larger cross-sectional area to a pipe with a smaller cross-sectional area, then the velocity of the water will increase as the cross-sectional area of the pipe decreases. This has to do with the principle of mass flow rate and how it remains equal throughout a pipe system, which you will learn about in this course. You will also learn about Bernoulli's principle, which states that the higher a fluid's velocity through a pipe, the lower the pressure on the pipe's walls, and vice versa. This helps us predict the pressure caused by fluids in motion in the pipe network. The study of fluid mechanics has an obvious application in designing water distribution networks, but there are other applications such as designing aircraft, which leverage the principle of Bernoulli's equation. When an aircraft is in flight, the pressure beneath the wing, where airspeed is relatively slow, is more than the pressure on the upper surface, where airspeed is faster, due to the curvature of the wing. This difference in pressure creates the lift force that keeps the aircraft airborne. Then, depending on what school you attend, you'll also probably have to take a few system design courses where you focus on applying all the principles you learned in your previous courses to design actual mechanical systems with various machine elements and components such as threaded fasteners, power screws, springs, gears, bearings, and so on. You'll learn how to select various elements to optimize the design of your system while also taking the cost of materials into account. In these courses, you'll find yourself designing manufacturing systems, control systems, thermal systems, and more. This covers all the core coursework you'll see in a typical mechanical engineering curriculum. Once you have completed all your core coursework, you'll have the option of taking additional elective courses. Some of these options may include stress analysis, finite element analysis, mechatronics, petroleum engineering, nuclear energy, composite materials, and much more. I hope this video has helped you understand what you can expect to study while pursuing a degree in mechanical engineering and the types of careers you can expect to go into. If you enjoyed this content, don't forget to comment, like, and subscribe. Thank you all for watching, and I will see you all in the next video.